This video provides an in-depth technical exploration of the MTS mechanical hardware in the loop, or mHIL, damper test system. The mHIL damper test system is a proven solution to a growing array of complex vehicle development challenges. It provides development engineers with a vehicle-level simulation environment which can be used to benchmark, characterize, set up, tune, and validate new vehicle technologies, such as semi-active or active dampers, suspensions, and body control systems. With proven mHIL hybrid simulation technology, the system can be used to enhance CAE model development, conduct accurate simulations earlier in the development process, and dramatically reduce track testing costs. So mechanical hardware in the loop is where we try to replicate what we do in a real vehicle system with a simulated vehicle system. If you look at the pictures on this slide in the lower left, on the typical proving grounds or out on the test track, you'll take a vehicle maneuver and the vehicle driving over some kind of road surface, give these as inputs to the real vehicle, and look at some kind of vehicle response. With mechanical hardware in the loop technology, we create a simulated vehicle system that has the same inputs, the driver input maneuver and the road surface, the same desired output, a vehicle response, but this is a simulated vehicle system with a virtual vehicle model combined with a component, or what we call a loading rig, in this case a damper test system. So the mechanical hardware in the loop in this case is the dampers themselves. You can see 4 frames on the loading rig. This is giving inputs from the model over to the damper rig, and there's feedback from the damper rig back to this vehicle model, creating a simulated vehicle system that replicates the work you can do like you would do with a real vehicle system out on the real world driving or proving ground testing. So it allows you to do vehicle level evaluations with only a model of the vehicle and a real damper subsystem of parts. The main system components, if we start from right and go left here, as we talked about the loading rig, today we're going to show you an electric EMMA loading rig, which is an electromechanical actuation rig. This is controlled by a loading rig controller. There's also an integration and user application interface in the center here. That's what ties the virtual side on the left, or the modeling and real-time technologies, together with the mechanical test technologies on the right-hand side. These are typically items provided by MTS. On the left is third-party, or it can be customer scope items, or provided by MTS. They're third-party items. For example, the real-time vehicle model software on the left there, the real-time simulator, which we call RTS or HIL system through this PowerPoint, and the software that runs on this system. In this case today, we're talking about a D-Space Galexio system, and you can see there's an ECU above it. There's an option for ECU integration if you're doing semi-active or active dampers. So these are the components that make up this hybrid simulation system from MTS. The signal flow for this system, that's starting at the upper left. You have driver inputs that go into the vehicle simulation model. The virtual vehicle model responds to these inputs, and we send a damper displacement input to the right in this diagram over to the loading rig controller, which gets sent over to the damper loading rig. This damper displacement gets inputted to the damper. We measure the force from the damper in real time and send this back to the virtual simulation. Ultimately looking at the bottom here, a vehicle or a component response of a vehicle level, or a component response of including the dampers in the loop with the vehicle model. As you can see above the real-time simulation system, there can be an ECU. Today's demonstration, we don't have an ECU, but there could be an ECU in the loop there. And as shown in the center, we have this mHIL damper and hybrid simulation user interface. We'll give a demonstration of this today, but it really is overseeing what's taking place across from the right and the loading rig all the way to the left, the real-time simulation system or HIL system. So I overviewed the system by PowerPoint. Now we'll come down on our floor for this demonstration to show you the physical components that make up the mHIL 4-corner damper system. Starting with the EMMA damper frames themselves. So here's 4 damper frames. We have the right front, right rear, and left rear corners of the dampers and struts installed as they would be in a typical vehicle. Within the EMMA electromagnetic actuation damper frame itself, we have the EMMA electric actuation device down here, which has a high-speed displacement feedback encoder as well. And shown in the front here is a static support cylinder. This is to offset the mean force of if you have springs installed on your dampers or on your struts, to offset the mean load that those would apply, so the electric actuator only has to move the dynamic load. Moving up from the base of the electromagnetic actuator, we have the specimen area itself. In this case, we're showing the damper installed. Again, displacement input from the lower part of the electromagnetic actuator itself. There's fixtures at both ends of the damper to attach it into the EMA damper frame. The lower fixture here is a unique fixture that allows us to attach in through the bushings. So we have the bushings included when we run our simulations. The upper is a hard mount of the body, so there's a small fixture to replicate that boundary condition. You can see at the top we have a load cell. This is for force feedback. So we have a displacement input and we have a force feedback. The damper is attached into a frame with 2 columns and a crosshead. So the crosshead shown here today is a manually adjustable crosshead. You can manually adjust it for different heights of damper specimens. This crosshead is a manually adjustable up and down with manual locks. We also have options for pneumatic or electric actuation up and down to adjust it, and electric locks. Also shown in the test specimen area is an infrared sensor. This is monitoring the damper temperature to get the damper set up to initial conditions before you begin testing, or while you're running characterization testing, you can monitor the temperature to make sure you don't exceed the temperature or have the desired characteristics you're looking for. Backing out, one more thing, we have a CE rated enclosure that encapsulates the test specimen area. We have the doors removed for clarity in this demonstration, but this enclosure is CE rated for human occupant safety around the test system while it's operating. Backing out, we have the drive amplifiers located inside of drive cabinets that drive out to the electric actuation. On this side of the system, we have our FlexTest digital controller, which is used to control the loading rig inputs and outputs. It also has a communication interface and clock interface over to our real-time simulator system from DSpace. This case is a DSpace Scalexio system. This is where the real-time vehicle model software runs. In the demonstration today, you'll see CarSim running. The real-time, these are both controlled by a real-time system user interface, which has software for both DSpace and the real-time vehicle model software, again, in this case today, CarSim, that run down inside of the real-time simulator. And we also have a user interface for the loading rig itself and the application for our mechanical hardware in the loop system that will get Tom Stachel will give an overview on today. This slide is showing the electric mHIL 4-corner damper system, lab layout and components. Focusing your attention at the center is the MTS 4-corner damper test rig with electromagnetic actuation. These 4 corners are mounted to a T-slot bed plate to react the forces generated during system testing. The electromagnetic actuators are fed from a power distribution cabinet that feeds into an isolation transformer, the MTS drive cabinets, and then out to the individual EMA corners. The corners are conditioned and controlled through the MTS control console and MTS user interfaces shown at the bottom of the screen. And the real-time user interface is an interface to the electronic control unit hardware that's used to condition and control the active or semi-active components on the dampers. To the left of the screen is an air compressor used for cooling of the system. And to the right of the screen are all the components labeled on the MTS EMA suspension test system. MTS also has an mHIL 1-corner damper test system as shown here. In this case it has one EMA electric damper frame, but the infrastructure of the system is very similar. There's a drive cabinet with a drive amplifier for this electric actuator, power amplifiers, wiring and cables, user interface, real-time system interface, and the MTS control console, and peripheral devices like the air compressor. So overall, same architecture, just 1 corner versus 4 corners. We also have an MTS hydraulic mHIL 4-corner damper system. This is showing the typical lab layout. Again, similar components with the 4 damper frames at the 4 corners of the vehicle. In this case, it's providing a hydraulic actuation versus electric actuation. And the devices to support that are a hydraulic power unit. You can see hoses distributing out to the 4 corners to feed oil to the hydraulic actuators at each of the 4 corners. Some customers may ask, what's the difference between electric versus hydraulic? If you've got an existing test system that's hydraulic, we can integrate mHIL with that. If you have one that's EMA, we can also integrate with that. If you're buying a new system, we need to talk about the application space of what you're trying to test. If there's applications, for example, for things like durability, we may consider a hydraulic actuation system over an electric system. So we need to have that application discussion with you to decide what system will be best suitable for your needs. So mHIL damper system applications, what can the system be used for? It's primarily used for active, semi-active, and or passive damper or strut development. A lot of customers use it for maneuver-based testing for vehicle level and subsystem evaluation, especially around like semi-active and active damper evaluation. It can be used for damper algorithm development for those systems. It also can be used for component evaluation and correlation of the damper components themselves, either comparing to virtual models that you have or, for example, to desired characteristics you want to see in the proving ground at the vehicle level or the component level. Supporting your track evaluation program. So maybe you have a new technology like a semi-active damper system that you've developed new control algorithms for and set up for. You want to go out to the test track and prove that out, but you may find some issues or challenges you run into. You can come back and use the system as a tool to support your track evaluation. One large advantage of the system is its ability to do fault and limit handling tests. So these on the test track can be very dangerous events in some cases if you're going up to a rollover propensity test or some kind of limit handling event, or if you're introducing faults into the ECU or damper algorithms of some kind. Out on the test track, depending upon how the vehicle responds, could be a very dangerous situation, but in the laboratory we can evaluate these events in a safe environment. It also can be used for traditional damper characterization, so things like force velocity, force displacement curves, including things like force and friction evaluation. We have, for the hydraulic actuation system, we call a moment input fixture shown here in the lower right. This is a fixture that provides strut moments. These moments are equivalent to the lateral force that would be applied to the tire patch during a cornering event, for example. The virtual simulation model can calculate this moment. We can apply this moment physically into a McPherson strut specimen, as shown here. This is important to get the right friction characteristics in the strut assembly during testing. As an option, we have environmental simulation, where we can integrate environmental hot-cold simulation around each of the dampers at the four corners. And the system itself can be expanded for use in ride, road, and four-poster simulation as well. What are the mHIL damper system benefits? There's three primary benefit areas: enhancing your CAE, accurate testing early in the development process, and reducing your overall testing costs. On the CAE part, you can collect enhanced characterization data used for your model development to enhance your model. And you could use CAE more in the front end of the development process to get more realistic answers earlier in the development and run faster validation cycles. With the system, you also can get accurate testing earlier in the development process. You don't have to wait for full prototypes and road load data acquisition. You can run earlier in the development process with the overall goal of your first prototype when you get to test track validation satisfies the targets you had established up front. It can be used for evaluation and validation at both the component and the vehicle level. One key aspect of the system is very repeatable. If we compare it to a typical track program, the ability of the driver to follow the same inputs, the same track trajectory, weather conditions, track conditions can change during the day, where this system in the laboratory is a very repeatable tool. It also allows for rapid testing of platform and geographic variations. If you have different vehicle weight distributions or characteristics of the vehicle that change on a platform between different geographies, you can easily test these different inputs by simply changing out the components or conditions within the vehicle model. You also can evaluate expected and unexpected fault conditions, again, as I noted before, easily and safely in the laboratory. Overall goal is reducing testing costs, reducing the number of vehicle prototypes required, the vehicle instrumentation and data acquisition costs that goes with utilizing those vehicle prototypes, and the track dependency. So now we'll switch over to a system itself where we'll go through a system demonstration. We already gave an overview with the camera showing the main system components, but we'll give a user interface overview and highlights, talk about some of the benefits of that system, how it's a one-stop setup, operation, and a place to do all of your setup, operation, and processing work from. We'll set up and run several vehicle maneuvers, including a sign steer, double lane change, and a ride road. And we'll review some results from these maneuvers to show you an idea of what the test data looks like and what you can collect for information from testing with the system.
I'm going to give an overview of the model side of the mHIL four-corner damper system. For this particular case, we are using the DSpace MATLAB and Simulink environment to integrate the vehicle model with our test rig. What I'm showing here is the Simulink model where we do the integration between the vehicle model and the inputs and outputs from our rig. So I'm going to dig down to show you where the vehicle model is. Here you can see the CarSim S function. Basically this is the core of the simulation, and as you can see there's some inputs going in. Those inputs come from our test rig, and there's also outputs going out of the vehicle model which go to our test rig. In this particular case, the most important signals are the damper displacements that we send to our test rigs as commands for the displacement, and the most important inputs are the forces coming back from the load cells that measure the damper forces, or if there's a spring, also spring forces. This is the CarSim user interface where users set up vehicle maneuvers and vehicle parameter sets. We're using a standard D-class vehicle parameter set for this demonstration. Typically users will have their own vehicle parameters. Those vehicle parameter sets contain suspension parameters, KNC data, tire data, and in this particular case we don't care so much about the springs and dampers because those are going to be on the test rig. We set up special maneuvers that allow us to put the model in the loop with our rig. So typically the sequence is that the simulation gets started and it pauses immediately to wait for the test rig to be put in the loop with the model. After that, we can select a particular maneuver from within a set that we have already set up. As you can see here, there's a number of maneuvers that can be run, and this is totally optional. We can set it up according to the particular user needs. So what we do is there's an input coming from our controller that selects one of these possibilities to run a maneuver. Moving on to DSpace Control Desk. This is the application that we use to communicate with the real-time model, which is primarily used for debugging purposes. This is not really needed for running the system, although many users will use control desks for things like looking at signals maybe from the CAN bus and things like that. For this particular application, we have passive dampers, so we don't really need it. But as you can see, we have a bunch of signals from the model and from the rig that we can look at here, and we also have the possibility of doing local control in case we don't have the MTS system running. So for debugging purposes, we can do all kinds of things with this application. Finally, there's an animation that is very useful to see how things are going. Sometimes, things are not running well, and using the animation, we can help debug what's going on. The last thing I wanted to add was that in the Simulink environment is where not only we set up the communication with our test rig, but users will also set up if they have any particular I/O that they need to set up in order to communicate, for instance, with CAN bus, or if we need to send signals to an ECU, a particular controller, this is going to be done in the Simulink environment.
All right, I'm going to show you an overview of the interface and the operation of the mHIL four-corner damper. What you see here is a controller that has been customized or tailored for this application versus a generalized controller. So as such, we've got a number of screens and features, functionality built into the system based around the concept of putting the vehicle model in the loop, in closed loop, with the physical dampers. So to start out with, An important aspect of making this work, of putting physical dampers in the loop with the virtual model, is to make sure that the two systems kinematically are correct. So when we put the dampers in here, we don't traditionally go just to a mid-stroke position and call it good. What we will do is match up physically with what the kinematic tables in the damper, in the vehicle model are set up for. We want to make sure that the ride height is at the correct position within the damper. We want to confirm that the stop engagements on both the jounce and rebound are engaged at the right points, so that the system will behave as it would be out on the vehicle. So that's what I'm showing right here. So when we set this up, we set up a home position. This home position is, as I described, matching what is set up within the simulation itself, or what we're taking off of a KNC, but typically it's just the simulation of the kinematics. So in addition to a home position, we are going to record a home force. Most of the dampers will have a pre-charge. We want to make sure we capture that pre-charge in here, as well as anything else. When we use an mHIL system, taking a physical component, put it in the loop, closed loop with the model, we want to include as many components as possible because those are not represented in the vehicle model. So we'll include the lower mount, the upper bushing mount, so that all of that is in the force that is going back to the vehicle model. I have a manual control capability here, so this simply allows me to manually drive each of the corners. We have a function generator associated with each corner. We also have the ability to drive them with a time history. This allows us to do traditional characterization. This is a dedicated mHIL rig, meaning it's intended to be run with a vehicle model, but it is also a damper rig. So it can do all of the traditional damper characterization that you normally do with the rig. We can run the sine sweeps, a sine input, a velocity input to do the characterization and build up tables on the dampers just as you would with a normal rig. But again, our focus is to put it in closed loop with the model. So if I demonstrate here, here's our channels. We've got the four corners, obviously, this being a four-corner damper rig. For each corner, we've got our vertical position. That's our primary control position, as Ford Boone described in the presentation. From the vehicle simulation, once it is started, we are going to be getting a position coming from the calculations out of that model for the damper and return the force. We've got down here, I'm going to move to the static force that was also presented by Ford, the static force to allow us to handle the base force provided by a spring. We don't want to use all of our energy in these permanent magnet motors to hold a high static force, so we take advantage of this pneumatic channel. And then there's a road position. The road position is actually a virtual channel. This gives us the ability to drive at the contact patch of the simulation a vertical input. We're going to be demonstrating this in just a moment. I've got the ability to turn on the data recorder, and I'm going to quickly bring up a screen here. These are all the channels that we can collect. So as was mentioned earlier, one of the components required to build an mHIL system is a very high-speed digital link between our D-Space hill simulator and our control system. Across this thing gives us the ability to send a number of signals in addition to the required signals for the closed loop, the position and force. If I take a look at the left here, these are all the physical signals that we have available to us, or calculated signals, but these are specific to the damper and specific to the load frame. We have our position, our force, our velocity, a number of internal control channels. We have our road channel, which again is a virtual channel, and then that specimen temperature that we can monitor. And we have this for each of our four corners. We have a driver. We have a number of user channels, and these are not physically present within the controller, such as an analog. These are mapped in that shared memory, that interface between the vehicle simulation and the physical system. So a customer may want to collect a number of additional signals that are in the model, or maybe associated with a block that they've added to the model. So they can go into the Simulink environment and map these channels. In this case, this customer is primarily interested in ride, and so we've got a number of accelerations here that are coming over in addition to the traditional channels we collect. Progressing across to the right, we now see the virtual corner signals. So this is the command coming to us from the vehicle model, as well as some of the simulation signals that we can collect. Since we only have dampers, we are collecting a spring force that's coming out of the spring table still present in the model. If we were to have a coil-over damper or a strut in the system, that would be removed as well for the simulation. I've got the other corners here. I'm going to conclude with this last channel. This is a number of the vehicle level signals that we can collect. If you are interested in doing tuning, if you're interested in doing end-of-line road program work, you're going to be interested in looking at how the vehicle is responding to the damper, and this is a number of those signals that you would be interested in. At the CG, we've got velocities, we've got accelerations, we've also got your typical roll, pitch, yaw angles, as well as rates. So any of the metrics that you typically collect for your ISO handling maneuvers or whatever events that you record on the track, we've got the ability to record this all together in one synchronized data file. With that, I'm going to just close this off and return back. One other primary tab that I want to go over is the simulation tab. This is essentially a manual control tab for the mHIL, for the simulation. Juan went over the adaptation that takes place that's required to put the dampers physically in the loop with the rig. There's another adaptation that we do. There's actually two aspects of it. There's the modifications to the model to take an external input and use that in replace of internal calculations or maybe a table. But also we put a wrapper around that model. This allows us to coordinate or supervise the process of putting the simulation in closed loop with the rig. On the bottom here, I've got buttons that represent that sequence. So to start out the process of putting it in the loop, the first thing we're going to do is we're going to initialize or start that simulation. And as Juan had demonstrated, this is the same simulation start that you would do normally offline with any of your vehicle models. Typically it picks the vehicle up virtually in the air, drops it, and the suspension and system will settle in at a ride height based on the laden condition of the vehicle. But typically the simulation will start at that point. Here we've got a special maneuver and a flag that holds that maneuver. We want to hold it in place because we've got the next step that is required, which is the equalize. In equalize, what we do is we take a look at what the physical system is set at and what the virtual system is set at. The physical position will likely be different than what the model is reporting for damper position because it's going to be based on spindle height or some other reference line within that simulation. We have to equalize those two components so that we can then make the command and feedback source switches, which are the buttons we have up here. This button is what's going to change our internal command switch from the function generator or just our internal set point to the vehicle model coming over that high-speed link. This button in turn also switches the command, the feedback source from the vehicle, from the model to the damper frame. So we're going to be taking the physical force measured from the damper frame based on the velocity input to the damper. We have a few more controls that we can take, which are, for example, the road. As I said, we're going to be demonstrating that in a ride event. We can take over steering input if we have a time history of the driver on the proving ground and we want to play exactly that out. You obviously can put that into the simulation, but we can drive it externally here. To go through a number of maneuvers, sometimes we want to, for example, change the vehicle speed. We've got the ability to do that, and we can run a maneuver at 40, 60, 80 kph, much as you do out on the proving ground. Once we have made the switches for command and feedback, then we're going to start the simulation. One point I want to make here is everything that I've demonstrated on the interface or shown you, both in the manual control, both in the manual simulation control, can be automated. And this is our normal mode of operation. So with this, I'm going to go to the auto test control, and we can build up a test script or a test sequence that is essentially an ASCII file, a very simple programming language that allows us to sequence and automate the process of starting the system, going to the home, walking through that sequence, and then starting the maneuver, starting our data recorder. And that's what we're going to do here. I have queued up a ride road, and all I'm going to do is select here the specific sequence associated with that ride road, and I'm going to push run, which will start that event. We're going to turn over to the recording now of the actual rig, showing you the ride road. But let me start with just describing what happens. So we're going to go through that sequence. We're going to initialize the model. We're going to go through the equalization. We're going to go through the switching of command and feedback sources. Once that's complete and we get status back that everything is correct, we're going to start the maneuver and the vehicle is going to accelerate down the road, and whatever lateral or longitudinal inputs that are programmed are going to start. And here we go with the ride road. Ford presented in his introduction that we would run through 3 different events. The next one we're going to run is a double lane change. So I've queued up the double lane change. I'm going to select this test sequence associated with that and push run. Now again, what's happening, what you can see on the scope, we'll be turning back to the machine quickly, is us stepping through that sequence again of initializing, doing the equalize, making the source switches, and then starting the simulation. So now we can see the vehicle is in the loop. It is now accelerating up to the steady state speed for this lane change. We can see the shift points that are in the transmission as we accelerate up. We're going to take the vehicle up to 100 kph, and then the lateral or the driver input will come in and run an open loop double lane change. All right, the lane change is complete. We receive a flag or a status back from the simulation that the maneuver has executed. With that, we'll go through and automatically run through our stop sequence of restoring the command and feedback sources and stopping the data recorder, stopping the simulation. All right, the final maneuver that we're going to show is a sign steer event, a traditional ISO handling event. So I've got it queued up. Again, I'm going to push the run button. We are going to run the automated test sequence associated with that. I'm getting a warning here. It's just telling me that I'm about to overwrite my data file. For the purpose of demonstration, we don't care that we overwrite the data file, so I'm going to click that away. And again, we're going to walk through that sequence of initializing the system. Once that is started, we're going to equalize the physical with the virtual side. And once that is completed, we'll start the maneuver. We switch sources for command and feedback, and the maneuver will begin. All right, system is in the loop and the vehicle is now accelerating. We'll go up to 100 kph for this sign steer event. What you're seeing here on the screen are the shift point accelerations associated with that. All right, we're up to steady state speed, and now the lateral or the driver input will begin. And again, what we'll see is 3 sign steer inputs. Once those have completed, we conclude the maneuver. We get the status back from the simulation that the driver event has completed, and we will stop the process, stop the recorder, return everything back to its original mode.
These data plots display typical results that can be achieved utilizing the mHIL damper test system. The mHIL damper system can be used for characterization of the damper utilizing vehicle level maneuvers. If you reference the sign sweep steer maneuver and ride road plots, they show examples of this. These plots show damper component behavior while running vehicle level profiles. The mHIL damper system can also be used for traditional damper characterization such as force velocity or force displacement curves, as shown in the damper characterization plot. One of the benefits of the mHIL damper test system is being able to identify issues while running vehicle level maneuvers and then determining the root cause of the abnormal behavior through a variety of testing on the system. Looking at the vehicle level maneuver attributes data plot, you see a real example of a vehicle level maneuver identifying a funny pitch behavior of the vehicle utilizing the mHIL damper test system. This led to a recharacterization of the damper force displacement curve as shown in the traditional damper characterization plot, which identified the issue at hand. These data plots illustrate several of the many applications the mHIL damper test system can be used for.